All right, good morning, everyone. We're recording, so we're ready to get started. What we're going to do today is we're essentially going to wrap up all of the observations that we had on the first day of class. So we played the swap puzzle on the first day of class. We saw that if we changed the rules of the game, sometimes there was configurations we couldn't solve, uh, especially if we changed to the 3-cycle version of the game. We figured out that it seemed impossible to swap just two pieces by using 3 cycles. Well, that's what we're going to wrap up. All of those observations and everything, they're all going to get wrapped up today. And from the topics of today, we are going to have a complete understanding of the swap puzzle in all of its sort of various little incarnations that we had on the first day of class. Then, which we're not going to get to today, but then on Wednesday, we're starting the 15 puzzle. And the 15 puzzle is going to be the topic of Wednesday and Friday. So we'll get some exposure playing with the 15 puzzle, trying to come up with a complete understanding of how to solve it, solvability criteria, all of that's going to happen with the 15 puzzle. And then that'll sort of mark the end of the topics that are going to be covered on the first midterm. So then we'll have reading week, and then the first midterm is going to be following reading week. But we'll have done everything up to the 15 puzzle, which is chapter 9. And then the idea is the 15 puzzle is a planar puzzle. We're going to move on to the next planar puzzle, which is the oval track puzzle. And we're going to see that we're going to need a little bit more tools from permutations to figure out the oval track puzzle. And then once we figured out the oval track puzzle, we're going to move on to the Rubik's Cube. And that's going to move away from planar puzzles more into spatial puzzles. There's this third dimension and there's orientation of pieces. And we're going to have to develop a few more tools, and then we can analyze the Rubik's Cube. So we're stepping stones, and we're almost at the point. End of today, we'll have dealt with the swap puzzles. End of Friday, we'll have dealt with the 15 puzzle. So let's see where we're at. I'll just give a quick verbal reminder of the kinds of things we've done so far. So we've defined what a permutation is, and we've done it in such a way that we've defined a permutation as a function from a set to itself, and it's a one-to-one and onto function, so a bijection. So we can think of that as sort of mixing up the elements of the function. The first element goes to some other element. The second element goes to another element. So we're thinking of a permutation as a function, and that gave us the ability to compose permutations. And composition of permutations, or multiplication, as we called it, allowed us to do algebra on permutations. And it's through that algebra that we've uncovered things like the parity result. Permutations are either odd or even, and that every permutation is a product of 2 cycles. So you can always produce any permutation by just swapping 2 things at a time. And now we're going to look at the collection of just those even permutations, and we're going to see how they're related to 3 cycles. So last day we introduced these 2 sets, the set of even permutations, which was AN, and the set of odd permutations, which I've denoted by ON. So classically, the convention is the even permutations are denoted by AN, and the odd permutations, well, we typically don't denote them by a particular name because it's the even ones that are important, the odd ones not so much. And we'll see another way we can define the odd ones later on. So ON is specific to this course. If you go out into other classes that deal with permutations, they're probably not going to make special reference to ON. So why not EN? Yeah. So there's a history behind that. The alternating group, in fact, permutations in general, have a history in their relationship with polynomials. So if we had a polynomial with n variables, then the polynomials with n variables, we can look at polynomials that don't change when you permute the variables. So for example, if I had a polynomial, this is a good question, so I'm going off on a bit of a tangent here. Let me scroll down to the bottom. I don't mind going off on tangents. If I look at the polynomial p, which is x1 plus x2 plus x3 plus dot, 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 plus all the way up to xn, then if I permute the variables, this polynomial doesn't change. So any permutation of the variables, this polynomial doesn't change. So what we'd say is P is invariant under permutation of variables. For example, this polynomial Q is not. Maybe I'll just say Q is x1 times x2. That's not invariant because I could permute variables. In some sense, by permute variables, I mean that I can replace with my collection of variables x1 up to xn. I can replace any of my variables with any other combination of them. So in this one, if I replaced the x1 with an x3 and the x2 with an x1, for example, so my permutation is x1 is replaced with x3, x2 is replaced with x1, and then all the other ones get replaced with other variables, then this polynomial's changed. So this is not invariant under this permutation of variables. And historically, the polynomials that are invariant under even permutations have something to do with signs coming up and some alternating nature of signs. And that's where the term alternating comes from. It has to do with how permutations were first being developed in their relationship with polynomials of multiple variables. And so alternating came up there, and it's just stuck ever since. So even though a lot of people will study permutation theory and never actually study the corresponding polynomial theory that they were first used to sort of analyze, that they'll never come across this idea of alternating signs and whatnot. And so the term alternating tends to be mysterious, but that's sort of a bit of background as to where it comes from. It comes from some particular application, and so that's why we're not using E of n for even permutations. Alternating is a bit of a nod to history. Okay, so what are the properties of AN? The properties are that the identity is even, and the product of two permutations that are even the product of two permutations that are even is also even. So AN is closed under composition, and the inverse of an even permutation is even. So it's closed under inverses. And that's nice because in some sense it says like AN is its own little universe. I can't very easily break out of it. If I take two permutations in there and I multiply them together, I'm still in that universe. If I take a permutation and I compute its inverse, or I take its inverse, I'm still trapped in this universe AN. So it's hard to break out of it. Whereas, for example, the set of odd permutation, that's easy to break out of because I just take two permutations that are in that odd set, I multiply them together, and boom, I'm out of there. That produces an even permutation, which isn't in there. So this set AN has a nice property that it's closed. It's closed under composition. What we call it closed. It's closed under composition. You can't break out by multiplying two things together. You remain in there. And it's closed under taking inverses. And it also has the identity. And it turns out that these three properties are very nice to have of a given set under an operation. And we'll talk a little bit more about that in chapter 10, general ideas of sets that have these kinds of properties. But that's one of the nice things about AN. Is this closure. And so there's a note there that the odd set is not closed under composition, nor does it have the identity. So it doesn't have two of these nice properties that AN does. So AN is called the alternating group of degree n. And we have that its size can be calculated as follows. So that's theorem 8.2.1. How many permutations in Sn are even? It turns out exactly half of them are even. So n factorial is the size of Sn. There's n factorial permutations on n objects. And half of them are even, which means the other half are odd. So this is a nice counting result that tells us exactly how many even permutations there are and odd ones. And so what we're going to do is we're going to prove this. And I like doing this proof because it shows that even sort of simple, maybe for lack of a better term, even simple naive kinds of ways of counting are very powerful in these upper division math classes. And so the way we're going to count things is we're going to count like we would if we were a 3-year-old. When my kids were quite young, 3 and 4 years of age, we'd have them set the table. And it's interesting to watch them set the table for dinner, because typically they wouldn't go 1, 2, 3, 4. There'd be 4 in the family. They would go and grab a plate, and they'd go mommy, daddy, brother, me, or mommy, daddy, sister, me. And that means that they were actually not, in some sense, counting the number of plates that were going out, but they were just making sure that the number of plates on the table was equal to the number of people who were going to sit at that table. And so you see that often with kids as they start to name things as to where they're going. This is for Jaden, this is for Maya, and so on. And they don't go 1, 2, 3. Oh, how many people do I need to get toys for? No, they just name them off. And that's a very powerful idea in mathematics, because that's the idea of having a one-to-one correspondence between two sets. And the sets are equal size if you have this one-to-one correspondence. And so that's what we're going to be doing here. Yeah, exactly. I still do that now too. In fact, that's a very powerful way to count. You don't have to, if you think about it, the way that it's really happening is we've got a set A and a set B, and we're trying to show, the set A may be people, the set B may be plates, and we're trying to show that they're equal to each other. Why on earth would we need to go to another set, 1, 2, 3, 4, and sort of pass through that? Okay, the number of people, that's in one-to-one correspondence with the set of numbers 1, 2, 3, 4, which is in correspondence with the set of plates. There's no reason to pass through this third set to establish a correspondence between A and B. And that's this powerful idea that you can establish a correspondence by just coming up with a function that maps elements of A to elements of B and does it in a one-to-one and onto way. So let's do that here. I want to show that AN and ON have the same size. Yeah, exactly. It's, in some sense, it's what we're doing is an isomorphism. Isomorphism is a slightly deeper term in the sense that it's a one-to-one and onto correspondence between elements of the set, but it also preserves some action you have on those sets. So whether it's a multiplication that you're doing, or in the terms of graphs, if it's a one-to-one correspondence between the vertices, but it also behaves the same way on the edges. So isomorphism is really about same form, so same number, and has the same structure as well. So let's do this. What we're going to do is we will pair up elements of AN with elements of ON. So we'll pair up even permutations with odd. In other words, we're going to go with a little bit of a buddy system here. We're going to take every even permutation and assign a buddy to them from the set of odd permutations. And if every even permutation gets a buddy, then they have the same number in each set. And so if they have the same number in the two sets and they unite to all of Sn, then each one of them has to have half the elements that Sn had. So what we're going to do for this buddy sort of pairing is we will consider the following function, or what's called a map. So in pure mathematics, we often refer to functions as maps. So if you haven't heard the term map before, and you've just heard the term function before, map just really is the same thing. It means function, though it's typical to use it in pure mathematics as a mapping. We got a mapping between these two sets, a way to go from one element in one set to an element in the other set. That's our mapping. So here's our function, or our map in this case. We are going to take a even permutation, and we are going to produce from it a buddy, an odd permutation. And how am I going to do that? Well, I'm just going to use the only thing I really can use in the statement of the theorem. It's that n is bigger than or equal to 2. So I have at least two objects that are being permuted. And so that means that if I took an even permutation, what I could do is I could map it to, so this vertical bar with the arrow coming at it, that's now telling me what the function's doing. The function takes alpha as input, and then what it's going to produce as an output is the 2 cycle times alpha. So in other words, this is just telling me that f alpha is 1, 2 alpha. That's just another way to write what that's saying in function notation instead of arrow notation. Okay, now that we got to say, does this make sense? Is this function or mapping well defined? Well, since 1, 2 is odd, it's a single 2 cycle, so it's odd, and alpha is even, then 1, 2 alpha is odd. So that's good because it does tell me then that that permutation I wrote down, the 2 cycle times alpha, does actually live in ON. So this function makes sense. Alpha goes in and something odd comes out. So as long as something even goes in, something odd comes out. So this is great. That function makes sense. So we'll just write down that conclusion. So f does indeed map an to ON. It does indeed take an even permutation and produce an odd permutation from it by multiplying by 1, 2. Okay, so now I want to know, does this mapping actually produce this one-to-one correspondence? Is it like the people and plates? For every person there's a plate, and for every plate there's a person. So therefore we have equal number of plates to people. Is that really happening here? So let's see, is it one-to-one? Well, one-to-one just means that if I put two different inputs in, then I get two different outputs. So different inputs give different outputs. Or another way to say that is if I put two inputs in and they produce the same output, then they had to have been the same input. And so that's what we're going to state here. We're going to say, suppose I put alpha and beta into our function, and they produce the same output. In other words, if you think of the plates analogy, if this one plate I have is assigned to person alpha and person beta, well then person alpha has to be the same as person beta. They've got to be just one person. So that's really what we're saying here, is that if there is a correspondence between people and plates, and this plate is assigned person alpha and person beta, then alpha better be equal to beta in order for it to be one-to-one. So if the output of alpha and beta are the same, then we want to show that the inputs actually had to be the same. Well, that means then, let's just write down what f of alpha is. It's 1, 2 alpha. And let's write down what the output of beta is. It's 1, 2 beta. And if those two things are equal to each other, then we have left cancellation that tells us that alpha is equal to beta. So in other words, if f of alpha is f of beta, then alpha had better have been equal to beta. And so that tells us that f is 1-to-1. So it's a 1-to-1 function. Now I need to show that it's onto. So what does it mean to be onto? It means that for every odd permutation in ON, I can always find an even permutation that maps onto it. Or for every plate at the table, there's always a person who's going to be assigned to that plate. So let's get onto. So let alpha be an element of ON. Maybe I'll use beta, because just to change it up, I'm kind of thinking of alpha as these things in AN, so I'll let beta be one of the elements in ON. So let beta be an element of ON. Then I need to find something in AN that maps to it. But I know that if that's an odd permutation, then if I multiplied it by a 2 cycle, then that's going to be an AN. And that's precisely the element of AN that when I put it into the function f, I get 1, 2 times 1, 2 Oh, sorry, that should be a beta there. I'm putting that function into, sorry, that permutation into F, and I get beta out. So for an odd permutation beta, I'm able to find an even one that maps to it, namely 1, 2, the 2 cycle 1, 2 times beta is an even one that maps to beta. And so therefore, we have that there's a one-to-one correspondence between the two sets, so they have to have the same size. That was our counting idea. If I can find a one-to-one correspondence, so a one-to-one and onto function between two sets, then they have to be the same size. So the cardinalities have to be equal. And since their intersection is empty and their union is Sn, then that means that the size of An, which is the size of On, is exactly half the size of Sn. So it's n factorial over 2. And that's the end of our proof. Okay, so this is a proof which is quite normal to do in the case where you're trying to show two sets are equal to each other. If I want to show two sets are equal to each other, what I do is just try to find a function that takes elements from one set to the other set and does it in a one-to-one and onto way. Okay, so now that tells us a couple of things. Actually, it tells us not only are there the same number of even permutations as odd permutations, it also tells us something else. It tells us, I'll write it down up here, now that we've done this proof, what we can do is we can take the set An, and if for every element of that set I multiply it by 1, 2, so that's typically written like this, the permutation multiplied by the set, and this is really just denoting the set of 1, 2 times alpha, such that alpha is in An. That is equal to the set of odd permutations. And so this is more typical to write as the set of odd permutations. We don't need a notation O sub n now for odd permutations because we could just write it as a 2 cycle times all of An, times every element of An. That represents the set of odd permutations. And so that's a more typical notation you'll see moving forward into other courses if you come across these things. Okay, now let's do stuff with these even permutations. Okay, so we have now the knowledge of how to work with any permutation and multiply and find inverses and find orders. We also had this very important result that said for any permutation, you can factor it into 2 cycles. Now what we're going to work towards is trying to show that for any permutation that's even, so any even permutation, we can always factor it into 3 cycles. So that's what we're going to work towards. In order to get to that, what we're going to do is we're just going to get familiar with what even permutations look like. And to do that, we're just going to go through a bunch of examples. So list the elements of A2, A3, A4, just so we know what they look like. So A2, one way to do this is to list all of S2 first, which there's only 2 permutations on 2 objects, the identity and the swap of the 2. And then we identify which ones are even. That's even, that's odd, and so that means that A sub 2 is just the set of the even ones, so it's just the identity. And that matches our results from above because, maybe I'll write it down here, the size of A2 by our theorem above should be 2 factorial over 2, which is just 2 over 2 or 1. So that agrees with our result from the theorem that says, yeah, A2 should have exactly 1 element, and yes, it does. It's the identity. So what about A3? Well, again, I could write down what S3 is. This is 3 factorial elements. So there's 6 elements. There's the identity, there's 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. And then we could pick off the even ones. Well, the identity is even. A 3 cycle is even. This 3 cycle also even. But the individual single 2 cycles, the other 3 elements, those are all odd. So these are all odd. They're just single 2 cycles. 1 2 cycle. 1 is an odd number. So that's each one of them is an odd number of 2 cycles. So that means that A3 is equal to the identity 1 2 3 and 1 3 2. And again, what is our theorem telling us? Our theorem's telling us we should be able to work out the value of the cardinality without even having to work out all the individual permutations first. That tells us that it should be 3 factorial over 2, or 6 over 2, or 3. And in fact, it is. We found 3 permutations which are even. So again, that's just illustrating the theorem that tells us we can count how big this set is without actually having to list the elements. But for getting practice as what even permutations look like, we're going to list the elements. All right, next we are going to go with A4. Now, we could do it the same way. The first thing to note is that S4 is 24, and we could list all 24 elements out, and then half of those would be even, so there'd be 12 even ones, but I don't want to list these out. I don't want to list all 24 of these out. We could, but I don't want to. That's just, I'm going to have to list 12 extra ones that I'm not going to use anyway. So how can we do this? Well, we could just try to think about what the form has to be. So elements of A4, so they're permutations on 4 objects, so have the form. Well, what could they look like? Yeah, they could be 3 cycles, exactly. They could look like a 3 cycle. Those are perfectly good examples of the even permutations that would be in A4. What else could they be? Any other ideas? What's another form that an even permutation in A4 would have? The identity, yeah, there's going to be an identity as well. I'll sneak that one in the front here. So they could have the form of the identity. It could be 3 cycles and 2 2 cycles. Exactly, 2 2 cycles would also give us an even permutation. And when I'm writing these things down, 2 2 cycles, I'm really meaning that there are disjoint 2 cycles. So none of the 4 numbers are repeating themselves. And so what that means is we have exactly what our permutations are going to look like. A4 is going to be the identity. It's going to, maybe I'll list the 2 2 cycles out first. It could be a 1 2 followed by a 3 4. Or I could have partnered up the 1 and 3 with the 2 and the 4 as another partner pair. Or I could have partnered up 1 and 4 with 2 and 3. And in all 3 of these cases, the order doesn't matter in the 2 2 cycles because they're disjoint. So I could have written it 1 2 and then the next 2 cycle 3 4 like I did there, or I could have written it 3 4 1 2. Those are the same, so I can switch the order of the 2 cycles. It makes no difference. They commute with each other. They'll give the same permutation. So there's all the possibilities for 2 2 cycles. We've listed 4 permutations so far, so we know that there's going to be another 8 that we still have to list in order to get up to 12. These are going to be our 3 cycles. So we got 1, 2, 3. I could also partner up the 1, the 2, and the 4. Or I could partner up. That takes care of 1, 2 with anything else. So maybe I'll go 1, 3 with something else. So that's going to be our 1, 3, 4. So that's 1 through, that's basically everything I can get with a 1. So I get it partnered with, oh, actually that's not everything I get with the 1s, because I'm going to sneak a couple in here. Because when I partner up the 1 and the 2 and the 3 together, I'm going to bring this one down. I'm going to move some of these things around. The reason is because I've also got the inverses of these 3 cycles, which involve the same numbers, just in a different order. So I've got the 1, 2, 3, and I'll sneak in the 1, 3, 2 next to it. That's the inverse of it, but involves the same 3 numbers. And then I've got the 1, 2, 4, and I'll sneak in the 1, 4, 2 next to it. And then I've got the 1, 3, 4, and I'll sneak in the 1, 4, 3 next to it. So now those are all the ones that involve the number 1 and 2 other numbers. Either the 2, 3, which gives us the first 2, or the 2, 4, which gives us the second 2, or the 3, 4, which gives us the third 2. And so what's left is the ones that don't involve the number 1. So that's a 2, 3, 4, or a 2, 4, 3. And that's it for the 3 cycles. And that gives us our 8 that we were missing. And so there's all of A4. A4 consists of 8 3 cycles, 3 products of 2 2 cycles, and the identity. Let me just, could we count, I'll say count without listing. So can we count these without having to list them? Because I've said there's 8 3 cycles, 8 3 cycles, but I got that count of 8 by actually just listing them all out. Could I count these without listing? Well, a 3 cycle is going to look like that. And I have 4 numbers to choose from to fill those slots. So how many ways could I do this? Yeah, I could do 4 choose 3. So 4 choose 3. That's to fill the slots. So I've chosen the 3 numbers that I'm going to use. Now they're unordered because I used the choose notation. So I've chosen 3 numbers that I'm going to fill into these. Now once I have those 3 numbers chosen, how many 3 cycles could I make with them? Yeah, I can make 2. So once I've chosen the 3 numbers, you know, I got an A, a B, and a C, then that can produce 2 3 cycles, an ABC or an ACB. So we got times 2 for ways to order. Maybe I should have slid this over because that was really the argument for the ways to order. And that tells me that there are 8 3 cycles. 4 choose 3 is 4, the number 4 times 2 is 8. So that's one way to do it. And that's quite nice because it tells us that we can count these 3 cycles without having to list them first. But even more than that, if we are actually asked to list them, we know how to count how many there are going to be. There's going to be 8 of them, so that when I go ahead and list them, I know whether I've got them all or not just by counting up the ones I've listed so far. And if I only got 6 of them, I know there'd be 2 missing, and that might give me an indication of how to go about finding them. So we can do things like that. Maybe as a next example, suppose I wanted to count how many products of 2 2 cycles there are. Well, how could we do this? I want to make 2 2 cycles. How could I do that? Any ideas? So I'll indicate maybe one way to do this. I need 2 numbers to fill that slot, or those 2 slots. So of the 4, I can choose 2 of them to fill there. And then that leaves 2 left, of which I need both of them to fill that one. So that's the number of choices I could have to fill the first 2 slots and the second 2 slots. The problem is that I've actually now overcounted, because, for example, say the first 2 numbers I choose were 1 and 2. And so that leaves me 3 and 4 to fill the second 2 slots. So that would be a 1, 2, and then a 3, 4. But sometime later down the line, as I'm counting, I will pick 3 and 4 first, and I'll use those to fill the first 2 cycles, and then 1 and 2 to fill the second one. That gives me the same permutation because disjoint cycles commute. So I have to realize that when I count in this way, I'm overcounting by 2 because the order in which I write the permutations doesn't matter. So this overcounts by 2, and then order doesn't matter. So i.e. 1, 2, 3, 4 is the same thing as 3, 4, 1, 2. So that tells me that there are 4 choose 2, 2 choose 2, all over 2, or 4 choose 2 divided by 2, which is 4 times 3 divided by 2, and then times another 2, or 3 in total. So there's going to be 3 pairs of 2 cycles. And we got those 3, so we can count them without having to list them as well. Does that make sense? So it's first position fixed. That's why we multiplied by 2. In the first one, yeah, so you can think of it that way. Once you've picked your 4 numbers, so you've got your 4 numbers listed out. There are 2 ways to write them out. You can think of it as the first position is fixed, but then you have to say which one you're going to fix there. So one of the positions is fixed. It's really just the order of the other 2 that's going to make a difference. And so that's why we multiplied by 2. Okay, so we can count without counting. Count without counting. Sounds like an oxymoron, doesn't it? We can count without what's typically referred to as exhaustive listing. So instead of exhaustively listing out all the elements, we can still count how many there are by other means. So for example, let's count how many elements of order 5 there are in A8. So an element of order 5 in A8, of which we only have 8 numbers to use, has the form as a 5 cycle. It's got to be a 5 cycle. Yeah, exactly. Could be a 5 cycle. Now, or the identity. Yeah, thank you. Has the form or the identity. Thanks. Yeah, we can't miss that one out. Exactly. But we're interested in order 5. So an element of order 5 has the form, it's a 5 cycle, but the element has order 1. So it's not going to be of order 5. So actually we don't need it here because it's not going to have order 5. So we've got now the ability to count how many elements of order 5 there are by just counting how many 5 cycles there are. So I'm going to write the word the so it's a little bit more clear. The. So how many 5 cycles are there? Well, let's see if we can argue like we did above. I need 5 numbers to fill the slots. So we're going to pick, we'll do this in a couple of ways actually. So I don't want to just indicate that there's only one way to do this, so I'll try to do it in a couple of different ways. So we pick the 5 numbers, pick 5 numbers to make the cycle. So now we've got 5 numbers. Now I want to make a cycle with them. How many ways could I make the cycle? Well, I could pick any one of those numbers and stick it in the first slot. And that's not going to be restrictive in any way because, for example, let's say I picked the number I pick out of the 5 that I got was the number 4, and the other ones were 3, 7, 2, 1. So I picked one of the numbers of the 1, 2, 3, 4, and 7 and put it in the first slot. That's not restrictive in any way because this is equivalent to 1, 4, 3, 7, 2. Right? I can always shift the numbers around in the cycle and not change the permutation at all. That's still the same permutation. And that's one of the keys to keep in mind when you're trying to count these things, is that there's a lot of ways to write the same cycle. So what this means is I can pick any one of the numbers and throw it in the first slot. It makes no difference what that number is, whether it's the smallest or not. So maybe I'll just write this as an example. Think about this, and they are equal. So the emphasis here was on these two things were equal to each other. So once I pick a number out of the 5 that I've got and throw it into the first slot, it makes no difference which one it is. So I don't even need to say it's 5, choose 1, because it makes no difference what it is. I just put one number in the first slot. Of the remaining 4 now, I need to distribute them around the remaining 4 positions. That is where order matters. So what we do is of these numbers here, pick 5, we then put 1 in first position, and other 4 get permuted in remaining spots. So what that means is that there are 8 choose 5 ways to pick the 5 numbers you want, times 4 factorial ways to arrange them in the cycle. Pick 5, arrange them in cycle. And so that has a, well, we don't even need to work out what the value is, but I'll write down it is 8 factorial over 5 factorial, 3 factorial times 4 factorial. And so that's one way to write the answer. And we could simplify this a little bit. I mean, I could say that this is 8 times 7 times 6 for the 8 factorial on the top, because the 5 times 4 times 3 times 2 times 1, that would cancel with the 5 factorial on the bottom. And then I've got the 4 factorial on the top. That would cancel with a lot of the 3 factorial on the bottom and only leave us with the number 4. And so there is what our answer is, 8 times 7 times 6 times 4. That's how many 5 cycles there are. So I'll fill this in as that, that could be a counting method of 1. Maybe I'll say alternate method. Alternate, we'll put that in brackets. We'll call this method 2, maybe. Okay, again, I'm trying to count 5 cycles. So 1, 2, 3, 4, 5. One way to do this is to just list choices and say, there are 8 choices to put there. And then there are 7 choices of the numbers in which to put there. And then 6 choices, and 5 choices, and 4 choices. So there are 8 times 7 times 6 times 5 times 4 ways to fill slots in the 5 cycle. Once I've thrown the numbers into the slots, I now have to worry about, am I counting the same permutation twice? So again, look back at this up here. If the numbers I chose were 1, 2, 3, 4, and 7, and I was using those numbers to fill the slots, then right now this 8 times 7 times 6 times 5 times 4 is just the number of ways I can fill the slots, and it's counting all the different possible arrangements. So it's counting 1, 4, 3, 7, 2 as different than 1, 2, 3, 4, 7. And that's different than 1, 3, 2, 4, 7. And that's different than, so it's counting all of these arrangements of those four numbers differently. The problem is some of those arrangements of numbers are going to give the same permutation. So for example, I'm reading now in that pink sort of cloud-shaped bubble around the two permutations. If I put the numbers in order 4, 3, 7, 2, 1, that gives me the same permutation as putting the numbers in the order 1, 4, 3, 7, 2. So how many permutations have I overcounted by? By just taking the number of choices for each slot and throwing them in there, I'm overcounting the same permutation multiple times. How many times will I be counting the same permutation? So I'll give a bit of a hint here. If the numbers were 1, 2, 3, 4, 5. Yeah, exactly. Got some answers there. We count them. There's 5 of them that are going to be the same permutation. So for example, the numbers in that order. But then instead, writing the same permutation but using 2 as the starting number. 2, 3, 4, 5, 1. Or writing the same permutation with 3 as the starting number. 3, 4, 5, 1, 2. Or 4, 5, 1, 2, 3. Or 5, 1, 2, 3, 4. Those are all the same permutation. We can shuffle those numbers around in the cycle and not affect the permutation. It's the same permutation. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1. So that means I need to divide this number by 5 because this is our overcounting. And that means I'll put the equal sign on the other side now. We got the same answer. 8 times 7 times 6 times 4 over, well, no, over nothing because I just divided by the 5. And so there is our final answer. 8 times 7 times 6 times 4. And that's the answer we got above as well. So we can count them. In the first method, I said I want to fill 5 slots. So choose the numbers in an unordered way and then force them into the positions in some ordered way. Or method 2 was pick the numbers that I want to fill the slots in an ordered way and then divide by my overcounting because some orderings will give the same permutations. So a couple of ways to look at it. Don't get greedy at the start and then try to build the permutation up through ordering, or get greedy at the start and force an order on things and then worry about having to divide out by overcounting because you got too greedy at the start. And greedy is not a bad thing in this case. It's just you were trying to force an order on it at the start, and then you have to realize that not all orderings are going to give different things, different permutations. Okay, so now we are at the point where we can analyze the swap puzzle with that final variation of 3 cycles. So we know that every element in Sn, where n is bigger than or equal to 2, can be expressed as a product of 2 cycles. So we say that Sn is generated by 2 cycles. It turns out that every permutation in An can be expressed as a product of 3 cycles. So let's give a quick proof of this. Suppose alpha is an element of An, then because it's even, alpha can be written as tau 1, tau 2, all the way up to some even number. So we'll call it tau sub 2k minus 1, tau sub 2k, where the tau i's are 2 cycles. Okay, so I had to write my subscripts in a a little bit of a funny way in order to convey the fact that there's an even number of them. So there's 2k 2 cycles for some integer k. So 6 or 10 or 22 2 cycles. There's some even number of them. Now what we're going to do is we're going to partner them up. Tau 1, tau 2, tau 3, tau 4, all the way up to tau 2k minus 1, tau 2k. Now, I have to caution you on this notation. These are not 2 cycles right here, because the taus themselves are 2 cycles. So this is a partner. So we've partner 2 cycles tau 1 with tau 2, and so on. So all I've done is just regrouped and said, okay, I'm going to put the first two cycles together and make a partnership out of them, and so on. So we've got these pairs. Each pair, tau I plus 1, can be expressed as, so that's tau I plus 1. That's going to be a product of 2 cycles. So it's going to be, maybe I'll put a colon here because there's a couple of ways to do it. They could be, the first tau could be just the 2 cycle AB, and then the second one is also AB. Or the first one is AB and the second one is AC. Or the first one is AB and the second one has nothing in common with it, so it's a CD. So that's all the possible ways we could have two cycles being multiplied together. And that's what each of these pairs is. It's just something that looks like one of these possibilities. In the case that they're the same 2 cycles, we get the identity. In the case that they share one number in common, we can write it as a 3 cycle. And in the case where they share 2 numbers in common, I'm going to change the color here just for emphasis. It's not the intermediate steps that matter, it's going to be the end result. But if there's, in the case that there's no numbers in common, I can write that first 2 cycle as an AB, and then I'll write the second one as an AC, and then another AC, and then lastly CD. So what have I done? I've multiplied, or I've inserted the identity in a fancy way. And the reason I've done that is because now I can write this as the first 2 of them is the 3 cycle ABC, because the A is in common with both of them. In the second one, the C is in common, so I can write that as CAD. Or I could write it as ABC, ADC. So what does that mean? It means that for each of these pairs of 2 cycles, I can always replace them with 3 cycles. So alpha can be written as a product of 3 cycles. And that's because we just take any pair of them and write them by their corresponding 3 cycles as indicated there. So let's do one example and then that'll be it for today. So we want to write this alpha as a product of 3 cycles. Well, the first thing I notice, there is a 3 cycle already, so good, I'm not going to touch it. For the next one, I'm going to split it up into 2 cycles. And then I'll use my rewriting method above. For this one here, I could write it as a 285. For this one here, I can use that last result. That tells me that I can write it as 246 and then 296. And so there we go. We've written alpha as a product of 3 cycles. And that's it. That's our proof. Every even permutation is now a product of 3 cycles. So it's possible to write it as a product of 3 cycles. So I'll end there. We'll actually, the next slide was about coming back to the swap puzzle. So we'll do that at the start of next day. and then we'll get into the 15 puzzle.